Hey folks, great to be here in Lille. First time for me here. I come from Germany, from a very small town. So sorry, this will be in English. I don't speak French, but please bear with me. So this talk is about security architectures of password managers. So it will really be a deep dive. If you got any questions, feel free to ask them. The talk is separated in 3 steps. So after each section, you can ask questions if you like. Full disclosure, I am CEO and co-founder of a password manager, obviously, so I'm talking about password managers. But I will try to keep this as vendor neutral as possible. First and foremost, there is like 3 basic functionality a password manager should have. First, it should generate unique passwords per website. Then it should store these passwords. And third, it should use these passwords to log you in again, right? So that you don't need to remember all these passwords you have. The biggest challenge password managers have is to protect all these stored passwords. And normally they do this by using a master password. A master password is a very long and complex password, which is used to encrypt all your other passwords. And this is like the typical state of the art in password managers. So now the deep dive begins already. So how does it actually work? So if you look at the architecture of password managers, the master password is entered by users, right? And then that master password is used to derive a cryptographic key. And that key derivation is done by what they call a key stretching. I will later explain what that actually does. And that derived key is used to encrypt the password vault, the encrypted database, right? This is obviously a very simplified view, but that's basically how password managers work. In all modern cloud-based password managers, that encrypted vault is transmitted to the cloud to be able to synchronize all these passwords between all your devices. And the basic idea is that the provider of the password manager, the infrastructure provider, cannot access your password because they are encrypted using your master password. That's the fundamental idea of password managers, and that's what a lot of vendors call the zero-knowledge architecture. So, in December last year, the ICO fined LastPass. LastPass is one of the big American password managers, and ICO is the UK Information Commissioner's Office. LastPass was fined to pay 1.2 million pounds because of their data breach that happened in December 2022, so like three and a half years ago. So what's interesting here in that message is the ICO said there is no evidence that hackers were able to unencrypt customer passwords, and it's not clear that it's really that case, right? So let's go down here. There is an interesting paper that summarizes all what happened in that LastPass breach. It's called the Breaking the Vault paper. And there is a lot of evidence that not just the encrypted databases have been stolen by attackers, but also that attackers were able to brute force the master passwords. And why do we know that this happened? Because some customers of LastPass stored the cryptocurrency seeds of their cryptocurrency wallets inside LastPass. And after that LastPass breach, several months later, several of these wallets have been emptied. So there is a high suspicion that attackers were able to brute force these master passwords and actually use the decrypted information to steal cryptocurrencies. So what did these attackers actually do? So first and foremost, the attackers compromised the workstation or laptop of one of the LastPass employees. So they found a vulnerability in one of the LastPass employees' installed software and found a way through that employee to the LastPass infrastructure. And that way they were able to steal all the encrypted vaults from LastPass. So more concretely, it was a backup of all these encrypted vaults. The attackers now were able to steal. What they did next, is to try to brute force master passwords. And a lot of master passwords are just 12 characters long with with up and down characters, with special characters, numbers, etc. But still, if it's just 12 characters, you can just brute force it in your own attacker cloud, and it costs on average $100. Obviously, there's a huge deviation in, if I say average. But basically, if you have a lot of these vaults, you can try brute forcing them over time, right? I mean, there's nothing stopping you from just trying over the next years. So that's probably what the attackers are doing and what they're probably still doing right now since the breach. So let's go down deeper into the cryptographic side of this encryption technique. What is actually slowing down the attackers? And then we get back to the key stretching. I have that picture down again. So just to recap, you enter a master password. Key stretching is used to derivate a key based on that master password. And that key derivation should be slow, intentionally slow. Because if attackers try to guess the right master password, they should be slow in trying new iterations. What most password managers were using before the LastPass breach is PBKDF2, which is password-based key derivation function 2. And you can configure PBKDF2. You can say how much iterations PBKDF2 should do. And the configuration LastPass and also Bitwarden had back then was 100,000 iterations. And that was already no longer state of the art. So the OWASP already recommended back then 600,000 iterations. So this is definitely a problem. They should have increased the iteration side to cope with attacker hardware. They haven't done it. So typical key derivation or key stretching functions work on CPU, right? It's just time complexity. If you study computer science, you know the big O notation, that's time complexity. And if you increase iteration, it takes more time, it takes more CPU power, it gets more expensive to brute force. There is new algorithms out there. For example, Argon 2, which is the successor, let's say. There was a huge cryptographer competition of new password-based key derivation functions, and the Argon 2 function won. So Dashlane already adopted it in 2018, so that's pretty awesome. Dashlane did the right step pretty early on, but a lot of other password managers haven't caught on, right? So yeah, they should have, in my opinion. Then there's a special case I want to talk here about. 1Password. They also used PBKDF2 with 100,000 iterations. After the LastPass breach, they also increased it. But 1Password was also one of the exceptions that was still secure. Why? So let me tell you. 1Password not just used the master password, they used the second secret. And they call that the secret key. And if you have used 1Password, you probably know the emergency kit. It's like a piece of paper you need to print out, and on that emergency kit, the secret key is written down. And to set up 1Password from the ground up, you always need the master password and the secret key. And obviously, that means attackers who just stole all the vaults and are trying to brute force, they also need the secret key. And that secret key is only available on paper at the end user side. So 1Password is secure in case of a 1Password data breach. Pretty great, right? I mean, that comes to a certain cost. And the cost is usability. People need to print out paper, put it in their drawer. There's a second secret which needs to be used. Okay. So my whole talk was titled, Why is 2FA useless in password manager data breaches? And to answer that, we just need to think about the end-to-end encryption again. So everything is encrypted with the master password, but what you can do, you can optionally enable two-factor authentication in 1Password, LastPass, Dashlane. You can use a TOTP code, for example, a 6-digit code you need to type in. or you can set up a passkey for authentication. And typically, at least until like I would say 1 to 2 years ago, these two-factor authentication techniques were always just an authentication to the provider's cloud. So it's just an authentication mechanism to log into the provider cloud. It's not part of the end-to-end encryption process. So in the case attackers are successful stealing encrypted vaults, they got all the vaults. So all the two-factor authentication mechanisms of the end users are now useless. So they just needed to circumvent one two-factor authentication of that one LastPass employee to breach the cloud. So yeah, that's why I would say the two-factor authentication, which is optionally be enabled in password managers, it's okay, but it's not really helping in the case of a breach. So yeah, it's basically what I said. It's an issue. We should do better, right? It's 2026. So what we propose and what also other good modern password managers are now implementing is hardware-based end-to-end encryption. That means we and others are using the security chips, for example, in smartphones or in security keys, FIDO2 security keys, so let's say device-bound passkeys. It's a new word for it. These are used for the end-to-end encryption of the password vaults. And these are two-factor secure by default because the security chip inside that device is unlocked using face unlock, fingerprint, or PIN. And that's only done locally. So hardware-based end-to-end encryption is always two-factor secure by default. So that's great. That's what we should do in 2026. Because, again, comparing these two scenarios, on the left side, you have the typical master password-based encryption and the breach. On the right side, again, I would say a breach can happen. Yeah, the probability is high that at some point a breach will happen because the password manager is a high-value target. So we consider the first step possible. But the second step here is really difficult. You need to physically steal the end user's devices to be able to decrypt the vault, and you need the second factor. And consider the example of Apple iPhones. You have 10 tries, 10 attempts, until the security chip of the iPhone finally locks, and you cannot try again. So the attacker cannot do unlimited brute forcing of pins. They are restricted to 10 tries. So that's why hardware-based end-to-end encryption is marvelous. Yeah, that's part one. Just to give you a small overview, I would say in 2026, first requirement is that we do hardware-based end-to-end encryption with two-factor security. And if you check out, I put all the American competition here. 1Password, they now have this in beta. It's called Unlock 1Password with a passkey. What they mean is a device-bound passkey, right, on a security chip. Then Dashlane calls it passwordless login. LastPass calls it passwordless vault login. And Bitwarden SSO with trusted devices. And we also implement that by design. OK, any questions here for the first part? Nobody likes to. OK, feel free to come to me after the talk if you have deep dive questions. Second part of the talk. There is more stuff coming up in our segment of password managers. A lot of people are really looking at it right now. So there is a new paper, academic paper from ETH Zurich, and they uncovered different vulnerability classes inside password managers, and they segmented it. And they called it the key escrow vulnerabilities, vault encryption, sharing, and backwards compatibility vulnerabilities. And I wanted to give you an overview what the difference between these attacks is and what my personal opinion on these attacks is. So first and foremost, there is the attacks, what they call sharing. So what they say here is organization and shared vault compromise via unauthenticated public keys. So let's explain that. What password managers are doing, they are also using a lot of asymmetric cryptography to be able to share passwords inside a team. So for example, in our team, there's 3 people having access to our PayPal account, but it's still the same PayPal login, same PayPal password. So there is a team inside our company with these 3 people, and they can access the PayPal login. And to be able to do that, that team is a separated vault that is encrypted to these 3 team members. So the issue here is that the server decides what public key corresponds to which employee. There is no out-of-band public key verification mechanism in modern password managers, let's say. To give you more an example of where we have that, if you look at modern encrypted messaging protocols like Signal, WhatsApp, or even Telegram, you all, or SSH, OpenPGP already also have that, but Signal is the modern example. You have these key fingerprints, right? You can compare them, you can scan QR codes, and then you know exactly, okay, that kind of public key corresponds to Dominic. That would be public key verification. Modern password managers still don't have public key verification. To do public key verification, either we would need to load a lot of usability and interaction onto the user, which we don't like to do, or we need to introduce something like key transparency stuff. And that's really difficult to do. So that's why I would say, as far as I know, there is no modern password manager doing public key verification. So an active malicious server could replace public keys with different public keys. The important thing to understand here, there's a big difference between a passive attack and an active attack. This is an active attack. The server needs to be actively malicious and exchange keys with different keys. So yeah, so that attack is not in the threat model of password managers, and that's also basically the answer of all the password managers that have been checked here. It's just not in the attack model. Then there is key escrow mechanisms. Some of these are, again, based on the assumption that public keys should be verified. That obviously cannot be fixed easily, but other issues were just implementation issues of password managers, which have mostly been fixed. And then there is these 2 classes of attacks which are really difficult and not easy to fix. So the first is vault encryption. There are some attacks on the actual vault encryption. And the biggest problem is if you naively implement the password manager, you encrypt all the items inside a login individually. So you encrypt the username field, you encrypt the password field, you encrypt the notes field, you encrypt the TOTP secret field and stuff on and so on. So that's what we call an item-based encryption. And that's an issue because it allows certain attacks on integrity, on exchanging these items. You can probably just exchange the password and the username field, and the password manager will still accept it as correct information. So I recommend for a modern password manager to do vault encryption. So always encrypt the full vault, not specific items, to guarantee the integrity of the complete vault. That's really important, but that's also not easy to change because password managers are quite old. They cannot just simply change the infrastructure from yesterday to today. It takes some rollout time, re-encryption on the client side and stuff like that. Yeah. Again, also pretty important here. There is a lot of metadata that is stored by password managers. The easiest metadata to explain is the website, right? So LastPass, for example, didn't encrypt the website. So the attackers now have all the websites of the user, and they can probably do great phishing campaigns based on that information. You probably know the famous old speak of an NSA head of NSA. He said, "We kill based on metadata." So metadata is important. you should probably also encrypt as much metadata as possible. So yeah, obviously the last point is simple in terms of my recommendation. Don't use old cryptography. But in reality, it's not as easy, right? To get rid of an old algorithm, you cannot just remove it from your code base. You need to at least, I don't know, support it for 2-3 more years. Because only if the user logs in again to their account and decrypts their vault, only at that step, the client can re-encrypt everything with a new cryptographic algorithm. So crypto agility is really difficult to implement for a password manager. But yeah, at one point you just need to change, and at one point you need to just remove old algorithms and maybe even disable inactive users. Okay, so that's basically it from part 2. So that was the ETH Zurich paper on password manager vulnerabilities just from this year. So just a broad overview. 1Password fixed everything besides what's in their threat model, not public key verification. Dashlane did the same. LastPass and Bitwarden is still working on some stuff because it's really difficult for them to fix it. It's just not 90%. They cannot just do it in 90 days. It's really a lot of like plumbing in the security infrastructure and the cryptographic architecture. Okay, any questions here? I know it's a deep dive. Feel free to ask me later. Okay, third part. Probably pretty fast. Yeah. Okay, there is a study of the BSI, the German Federal Office for Information Security. In France, you got the ANSI, which is like the same but in French. And they published a paper where they looked at different password managers. It's a bit of a weird collection of 10 password managers. I try to find out why they selected these. And they said, yeah, we try to make a mix. But there are some really weird ones here inside. And I translated the table for you because it was in German. That's the output of Claude. So that's the Claude translation of the table. And the table is pretty big, but I picked out all the cryptographic stuff that's interesting for me. And there's like the basic requirement. All content is encrypted. And there's already a lot of no's there. That's an issue. And the second is a little bit of a difficult requirement. I will talk later too. But then the third one, manufacturer can access that data. That's so if all content is encrypted, that should probably be a no, right? There are some special cases here. But in general, if everything is end-to-end encrypted, the provider shouldn't be able to access this. And then the last one, are they using only secure, correctly configured cryptographic algorithms? And this study has been done by only looking at the publicly available data and asking the manufacturer a lot of questions. So the German Federal Government Office of Information Security, they haven't done a code check, right? They just did ask a lot of questions to come up with that table. And yeah, first and foremost, please don't use these, right? I mean, in my personal opinion, it's a basic requirement of a password manager to have everything end-to-end encrypted. And that's not just my opinion. You probably know next year, 2027, the Cyber Resilience Act will be in place. And the Cyber Resilience Act will say, hey, password managers, they are class 1. There's a special page about class 1 products and password managers are in it. And there's a new standard coming up from ETSI that specifically defines the requirements for password managers under the Cyber Resilience Act. And they will say everything needs to be end-to-end encrypted. So finally, all these will be no. In my opinion, they will not be allowed to sell next year after the Cyber Resilience Act. Let's see how that actually, if that actually happens. So please don't use these. So that's it. Okay, I have more time, so I can explain more what I find interesting. So there is the Chrome Password Manager and the Mozilla Firefox here. These are two password managers built inside your browser. And it's great that they included these. What is interesting here, by default, these two are not end-to-end encrypted. But you can enable that. So right now, if you're using Google Chrome, please go to the settings, go to the Google Password Manager settings, and then say, I think it's called client-based encryption, and then you can set up a master password for your Google Password Manager. And if you've done that, Google can really not access your passwords. Google is also trying different stuff to protect their passwords. They're doing hardware secure elements in their data centers to protect their secrets. So that's why at Google Password Manager here, you got a yes here down. They try to not be able to, right? Same is true to a certain extent for Firefox. You can also set up a client-based password or passphrase. I think Firefox calls it a passphrase. That's basically the master password that encrypts all your other passwords. You can also set up there. So they are pretty okay. Also, the answers from Google and Mozilla were pretty good. So that's fine. Yeah. Okay. So what we also got is KeePass2 and KeePassXC. These are the open source password managers, which are like single user solutions. You have one vault, one master password to accesses. You cannot share your passwords. They are also secure. It's pretty great. But what is about this requirement here? Because everyone in the table got a no except for KeePass. And that's a very difficult requirement, but I really like that requirement because it goes even deeper down the cryptographic theory. So, I already talked about modern messaging protocols like Signal, WhatsApp, Telegram is trying to do that at least to a certain extent. What they all do is forward secrecy and post-compromise security. It's two different requirements. So let's look at it. So if you're exchanging messages with someone on WhatsApp and you delete these messages afterwards, you can just go into chat and delete messages. The question is, will an attacker be able to decrypt these messages at a point later when your device is compromised? So if you write it down as time goes by, you first have the secure messages, then you probably delete some of these messages, then your phone got hacked, right? Or the phone of your recipient got hacked. And at that point, all your messages are insecure, right? They're eavesdropped by an attacker and can be read. So all the future messages are insecure. But if you have something called forward secrecy, at least all the messages that have been deleted are still secure in the past. And to implement forward secrecy, you need to do something that's called key healing. So you generate new cryptographic keys in points in time. So messages here are encrypted with different keys than message in the past. Only if that's implemented, you got forward secrecy. Then there's like the requirement that's from the other side, post-compromise security. That's even more difficult to wrap your head around. So again, you have the point in time where the device got compromised. Your WhatsApp is now insecure, let's say, and but okay, you found the malware, yeah, and the malware got deinstalled from your device. So are you secure again after that? And for this, you need post-compromise security. So there is some point in time, what we call the recovery, where so at some point here, the malware got deinstalled. So the device is now secure, but you know that the attacker now has some cryptographic keys. So there is recovery. New cryptographic keys are used to encrypt future messages, and now you're secure again. So these are two very interesting properties of modern end-to-end encrypted messaging protocols like Signal and WhatsApp. you always want to have forward secrecy and post-compromise security. Okay, I'm telling you that because what about password managers? So, forward secrecy. Does it make sense for password managers to have forward secrecy? Any opinion here? No, no. No, you don't. Because you always, even in the future, you want to access your old passwords. You're never deleting passwords in your database. So forward secrecy doesn't make sense for a password manager. But post-compromise security does. And that's actually what this this line in the evaluation said. Is the vault re-encrypted when the master password changes? So if you know your password manager has been compromised, so someone, you got malware on your device, or someone knows your master password, the intuitive way to fix it is to change your master password, right? But a lot of password managers are not re-encrypting the whole vault with the new master password. They're just derivating a new key and also using that new key to encrypt the vault. But it's still possible to decrypt the vault with the old master password. So a lot of password managers don't have post-compromise security. So to explain that for password managers, you have the legacy architecture. Let's say your old passwords have been breached, right? There is some point of compromise here. Attackers were be able to steal the content of your vault, and they are somehow also stole your key, cryptographic key or master password. And if you find out that this happened, you change your master password, and you probably also change all the passwords on all websites. Even if you do that, the new passwords inside your vault are compromised again, because the old master password can still decrypt the vault. So that's bad. In a modern architecture, we want to have post-compromise security. So again, like in modern messaging protocols, there should be some point of healing where the keys, the cryptographic keys to encrypt and decrypt the vaults are rotated. And if that's done, all the new passwords you store inside the password manager are secure again. So yeah, it's a little bit of a interesting property. I like it. You can do a lot of philosophical talk about that, how that actually happens. But it's an interesting requirement you can have. And yeah, one password, you can trigger that manually. It's not done automatic. If you trigger the recovery process in one password, key is rotated. By Dashlane is automatic key rotation, pretty great. And then LastPass, Bitwarden again, only manual. And I totally understand that this is the case. It's just very difficult to do. So yeah. Okay, that's from my side. Concluding the talk, there's like 3 requirements I would pose to modern password managers. First is hardware-based encryption for real two-factor security, vault-based encryption, not item-based encryption, metadata encryption, no legacy algorithms, and last but not least, post-compromise security for key rotation.
Thank you very much, Dominique and Shurman. Bravo.